In the last video, we selected a sample from our timeline, and I explained how to do the standard offset analysis up here. Now I want to explain how the steps work. Any given replicate analysis in Easotope is composed of different steps, and these steps are executed one after another. So imagine you've imported data from your mass spectrometer. You have a large table of voltages. Each of these steps are then given those voltages, and data is added to the table by the step. So the step might decide to add a new column and calculate some numbers and add that. Then the next step will do the same thing, calculate some numbers and add to it. So your table, with the execution of each of these steps, your table is growing and growing and growing, and you're getting more and more values in the table. So what you finally see when you look at your output, when you look at your results table, you see a huge spreadsheet of all the numbers that were calculated by all these steps. Easotope doesn't just give you the massive steps, though, the massive data. It actually lets you go through the steps one at a time and see what each step is doing. So there's no black box in Easotope. You can look as deep as you want down into the data, down into the calculations of every single calculation that Easotope makes. I'll show you how to do that now. So when we select a step, you see that some tabs just appeared up here that weren't there before. And those tabs are specific to a step. So whereas the first tab is specific to a correction interval, the rest of the tabs are specific to not only the correction interval, but also to the step that's being selected. So we can look at a step, and we can click on the documentation tab, and you see that each of the steps here, there's some documentation explaining what they do. So here we calculate the various carbon and oxygen values and the clumped values that we need from the original voltages. And this documentation explains line by line how to do that. So each of the steps is documented. You can look at them and see what does this step actually do, and you can verify the results yourself if you want to. If we look at the second tab, this is the input and the output. Now remember, I said earlier that each step is basically taking the results table and adding to it. So this here shows you exactly what it's adding. So these are the input columns here, the columns that are required for this step to do its work. So we see here that this step requires voltage is 44 through 49, and it needs reference and sample versions of those voltages. And then it uses that data and generates these columns. So it generates our clumped specific values and puts them in the table. So before this step does its job, this must exist in the table. After the step is done with its job, these will now exist in the table. So this is just a description of how your table is going to be modified by this step. Next, we look at the parameters field, and there's currently no useful parameters for this one, so let's go to the carbon drift correction. If we look at the carbon drift correction step, we can see the parameters for this are these here. You're allowed to specify, for example, what window around your sample you should use to collect your standards. So this is saying that I want a user-specified window of 3 standards before and after the sample that I'm correcting. Or I could also say use all the standards in the entire correction interval. So there's a little bit of choice there. Then there's a list here that explains which standards you want to use for your correction. So as your lab progresses, you might add standards or remove standards from your configuration. And here you can have the standards in the database without actually using them for your calculations. Maybe you don't trust them yet, maybe you're just getting used to them, something like that. So here you can activate and deactivate samples. But remember that this parameter is specific to this step. So a different list will exist for the oxygen. Okay, in this case it happens to be the same. But you could make your oxygen standard correction, your oxygen standards that you use for correction could be different than the carbon ones that you use for correction. And the drift correction also has the option to apply stretching or to not apply stretching, and that's explained in the documentation. Something that's very, very important to know is that when you're first configuring Easotope and you're creating new correction intervals, you haven't yet set up the parameters for the different steps in those intervals. So if you just create correction intervals and you start using Easotope, you start importing data, Easotope is going to give you output, but the output's not necessarily going to be what you want, because what you have to do is go through each of these steps and go through all the parameters and set them the way you expect them to be set. Only then, only after you've done that and you've saved them, will your data be correctly corrected inside that interval. Setting these parameters is a global thing. It's valid for the entire correction interval for all users. So only one user has to do this. And in fact, I recommend that only 1 or 2 trusted lab people have permission to do this, to modify the parameters. Other users can look at the parameters and make suggestions if they want, but your best people should probably be assigned to setting parameters like this. Another interesting tab after the parameters is the graphics. So each of these steps can give you a window into what they're doing, essentially. So let's go to the, it's not as colorful. Let's go to the oxygen drift correction. And we can see that in the parameters, stretching was turned on. So we have a graph with stretching applied here. We have 3 standards before and after our samples, so we should have 6 standards here. We have 1, 2, 3, 4, and then 5, 6. That's about right. There is one standard here that's being graphed, but it's disabled, so that one's not actually being used. It's just there to show you that it would be used if you were to enable it, so it's not actually in the calculations. Then we make the linear regression with those standards. The slope and intercept of the regression are shown here. Then we calculate a correction for our sample, and the correction value is shown here. So you're really getting every step of the way here. You can even scroll over these individual points and write down those numbers. If you wanted to do this calculation by hand, it wouldn't be that hard. You could pull the numbers out here, verify that the slope and intercept are correct, figure out the correction yourself, and then verify that this step is correct. The philosophy here is that Easotope does not hide anything from you. It shows you everything, so everything is verifiable, and that has the advantage of not only being good for you, but also being good for me as an Easotope developer. I can make sure that my software is correct. I am sort of recruiting all the users to verify that what I'm doing is correct in the software. So that's the graphics tab, parameters tab. Dependencies tab is less important, but still necessary sometimes. When a step is doing its work, it may need some external information, some information that's not in the table. So here we have, for example, the value of the ETH standards. If I'm going to graph those standards here, then I must have these values from somewhere. And those values are not in my normal results table. So I have to get them externally. I have to get them from the database sort of out of band, extra to my normal processes. So they're listed here as dependencies because they're inputs to the algorithm, even though they're not in our table directly. So if you combine the, if you look at the input-output, understand what's being written and read, look at the parameters, understand the algorithm, look at the documentation, look at the graphs, look at the dependencies, you should be able to calculate everything all by yourself. And the results tab show us what Easotope has calculated. So if we look at our input and output for this one, this is a drift correction. We're assuming an input of an acid fraction, an acid corrected version, and then we're generating a final version. If we click on results, we see that the acid version is here and the final version is here. So the results tab is showing us the table of results, but it's showing us only the inputs and the outputs that this particular selected step is calculating. So between all of these tabs here, you can drill down as deeply as you want, find out exactly what that particular step is doing, and then you can go on to the next step, the next step, the next step, and you can learn the entire data analysis and verify that the results are correct. Of course, you might have multiple data analyses here, depending on what are turned on for that correction interval. So you may be able to bounce back and forth between data analyses and see how the different analyses differ and things like that as well. So this data analysis screen is relatively powerful. It allows you to see as deeply as you want, gives you the information you need to make decisions about replicates being disabled, for example, or something like that, and gives you the confidence in using Easotope.